Hi there, welcome to the homeostasis simulation. Here you will learn how your body regulates many physiological variables to maintain a healthy equilibrium following external stimuli. As you know, the human body is constantly receiving stimuli from the environment, like a change in the external temperature. The body also needs to adapt to its own activity, for example when doing physical exercise. Maybe take a few seconds right now to feel your heartbeat. I am certain you can remember situations that made your heartbeat faster or slower, but it would always come back to a resting rhythm after a while, would it not? Despite these constant stimuli, the numerous body physiological variables stay remarkably stable, whether it is for example blood pressure, body temperature and many more. The body is actually always trying to achieve a delicate balance, maintained by a network of regulatory pathways that kick in when a stimuli throw the system off the equilibrium. This broad concept makes up what we call homeostasis. Okay, before we learn more theory, let's head over to our physiology area to test it out. Move to the physiology lab room by clicking on the large door behind Dr. 1. Today is a really hot and sweltering day, and it is quite uncomfortable to stay outside. Fortunately, we are taking shelter in this lab with an efficient air conditioning system. I am sure you have noticed Phineas, our virtual sample patient. We can monitor Phineas' body in real time when applying stimuli. Watch the middle screen in front of you. For now, we will follow 3 physiological variables over time, from left to right: body temperature, amount of sweating and blood vessels diameter. As you can see, in this stable and comfortable environment, Phineas' body temperature does not vary from the resting value. So what do you think would happen if we were to change the equilibrium? Turn off the air conditioning using the left screen. Observe the impact on body temperature. Logically, the body temperature is rising as the room becomes hotter. However, how does a body monitor its own temperature? How is it able to sense something might be going wrong? Do you think you can find the sensors for the temperature on Phineas' body? Find the sensors for external temperature by clicking on Phineas' body and clicking on the correct button. Indeed, the skin contains thermoreceptors, which are sensory nerve cells triggering electric signals when they detect a significant change in external temperature. For internal, core body temperature, there is another set of visceral thermoreceptors. Sensors, in a general fashion, are the first step of any regulatory pathway for homeostasis. They detect or measure the stimuli, and send a signal to a control center which will make decisions to counteract the stimuli. Now, can you figure out the control center for the regulation of body temperature? Find the control center for body temperature in Phineas' brain. That's right, the hypothalamus is at the receiving end of the thermoreceptors and can process the signal to take action and maintain the balance. This is the typical role of a control center in a regulatory pathway. In the meantime, the room temperature keeps rising and it might become dangerous for Phineas. Observe how the body temperature has increased. Oh no, Phineas' body is reaching its limit in heat tolerance. The hypothalamus will send signals to other organs, called effectors, to act to balance out this dangerous stimulus. Can you figure out what they are? Find the 2 primary effectors for regulating body temperature. You rockstar. The human body can indeed dissipate heat through the production of sweat by glands located all over your skin. The widening of blood vessels also allows a larger volume of blood to flow close to the skin surface, thus dissipating more heat at this interface with the external environment. Observe the impact of the effectors on the physiological variables. You can see that after the effectors kicked into action, the body temperature has stabilized, although it is not back to the resting value yet as the stimulus is still ongoing. This is a good example of a homeostatic system in action to maintain a physiological variable within a healthy range for the entire body. Switch the air conditioning back on. Observe the return to the resting range. Now that we have removed the source of the external stimulus, what do you think will happen? This is correct. The sensors, detecting that the stimulus has stopped, will send signals to the control center which will reinstate balance by stopping the action of the effectors. This phenomenon is called a negative feedback loop. In a negative feedback loop, the outcome of a process leads to a decrease in the initial signal. In contrast, which of the following do you think does not have a feedback loop? Absolutely. Out of all those choices, the voluntary stimulus to move the hand is not feeding a signal back to a homeostatic system. It is simply an action divided by reaction but not a loop. You have now been through the basic structure of a regulatory pathway in homeostasis: sensors, control center, effectors and a feedback loop. A feedback loop defines a system in which the output influences the input signal and thus can amplify or dampen the entire system. A biological system in a negative feedback loop would result in the decrease of the initial stimuli, leading the sensors to tell the control to diminish or cancel the physiological response. This is the standard for homeostasis, leading to a return towards equilibrium. A system in a positive feedback loop, however, would have an output amplifying the initial stimuli, leading to the sensors telling the control center to raise, sometimes dramatically, the response. The system would then drift further away from equilibrium and is thus working against homeostasis. You have now been through the basic structure of a regulatory pathway in homeostasis: sensors, control center, effectors and a feedback loop. Nice. Body temperature was a good and simple example of homeostasis, but there are plenty more and they only get more complex. Right now Phineas was just standing there. What if you were exercising in the same conditions? How is your body going to be affected and how is it going to react? Please take the time to observe the new physiological variables we are going to monitor. We now have on our screen, from top left, body temperature, amount of sweat, blood vessel diameter, heart rate, blood pressure. We will now disrupt the current balance by asking Phineas to do moderate exercise. Take a look at the new variables and their current behavior. What behavior do you expect from the heart rate and blood pressure variables during exercise? Interesting. Let's see for ourselves, shall we? When ready, switch to a moderate exercise level. Observe the change in the physiological parameters. Obviously the body reacts to the new stimuli arising from exercise by stabilizing the increasing body temperature at a healthy level. The heart rate increases substantially as well to provide more oxygen to the muscles for the workout, but blood pressure interestingly only increases very little. What do you think are the effectors causing this stabilization? Find the two effectors of blood pressure regulation. Absolutely correct. The heart beating faster or slower can impact the blood pressure in the arteries. The widening of the blood vessels, called vasodilation, on top of helping to dissipate more body heat, also decreases the pressure in the arteries and veins, thus maintaining a tight control on blood pressure. The body is now in a nice stable state, where the physiological values are not at their rest values but stable and allowing the body to continue functioning healthily alongside the stimuli, in our case the moderate exercise. Then should we crank it up to see what would happen if we increase the exercise intensity once more? Set the exercise level to high. Observe the outcome of the high-intensity workout. As we can see, the body temperature raised but was stabilized again with the sweat glands starting to act to release body heat, and the blood vessels widening even more to counter the body temperature and increasing heart rate. The stimuli is pushing the homeostatic system to its limit, but it is very much bearable thanks to the tight regulations. Can you find the sensors that are measuring the increasing blood pressure and the control center that sends signals to the heart and blood vessels? Find the sensors for blood pressure on Phineas. You are getting good at this. The baroreceptors in the aorta indeed measure blood pressure, then communicate to the medulla oblongata as a control center, triggering the pathways to regulate blood pressure within a tight range. Phineas has been exercising for a while now. What would happen if we made the conditions even harsher? Turn the air conditioning off. Observe the outcome on poor Phineas' body. Oh no, it looks like the homeostatic control cannot cope any longer with such drastic conditions. Phineas is now sweating heavily, his heart beats rapidly, the blood pressure increases dangerously and his body temperature reaches critical levels. He is actually in a state of shock. Quick, act to remove some of the stimuli before irreversible damage is inflicted to Phineas. Turn the air conditioning on and stop the exercise. It seems Phineas' body went into a state of shock. Why do you think this happened? Correct. The homeostatic regulation was working fine, with the sensors picking up on all the stimuli and telling the control center to act. However, it was the intensity of the response by the effectors which was not enough to maintain homeostasis. In this case, the body tends to switch to a positive feedback loop of disruption, where systems shutting down leads to more systems being disrupted. In our case, stopping the stimuli should have prevented the worst. Observe the return to normal homeostatic levels. Something is wrong here, the physiological variables do not seem to return to the resting values. Why do you expect this is happening? You are smart. There is indeed another regulatory pathway that has been affected by the exercise level and is preventing a return to rest values. In this case, it is likely to be the concentration of sugar in the bloodstream. Right now Phineas has used a lot of energy to work out, and the body is trying to replace the missing glucose to return to homeostatic balance. Anyway, well done for saving Phineas from dying. Let's now have a look to see how we can fix this blood sugar issue. Sugar is transported through the bloodstream to provide energy to tissues all throughout the body. However, while the blood sugar concentration varies throughout the day, it is critical to maintain a healthy range to prevent heart disease or diabetes. Observe the new variables we are going to follow up. You might have noticed on the right-hand screen that we have 3 new variables to keep an eye on this time: blood sugar, insulin and glucagon. What is called blood sugar is mainly glucose, carried through the bloodstream from the digestive tract to the remaining tissues in the body, constant need of energy. A low amount of blood sugar means organs cannot perform properly and leads to serious illnesses. On the other hand, excess blood sugar leads to storage in fat tissues and in extreme cases in deregulation of the blood sugar levels, such as in diabetes. Insulin is a hormone secreted in presence of high glucose concentrations in the blood that triggers its storage in the body in the shape of glycogen molecules. Glucagon is another hormone, but with the opposite effect of insulin. It triggers the conversion of glycogen back into glucose to be released in the bloodstream to rise abnormally low levels of blood sugar, for example when the body consumes it at a higher rate than usual. Sweet. Let's see if you can figure out the homeostatic regulatory pathway then. Find the sensor for blood sugar regulation. Well done. The pancreas, and particularly the islet beta cells, contains glucose receptors and transporters at their surface, acting as a sensor for the regulatory pathway. Now can you guess which regulation center they would send signals to? Find the control center of blood glucose regulation. Well done. The pancreatic islets are also the primary control center for blood glucose regulation. After receiving a hormonal signal from the sensors, the pancreatic alpha cells would secrete glucagon if the blood sugar is too low, and beta cells would secrete insulin if the blood sugar level is too high. Now what organ would insulin and glucagon affect? Find the effector of blood sugar regulation. Well done. Glucagon and insulin indeed act on the liver. Insulin would signal the liver to absorb glucose and store it in the form of glycogen to reduce the blood sugar concentration. Glucagon on the opposite tells the liver to convert the stored glycogen back into glucose and release it into the bloodstream to rise a failing blood sugar level. Now let's see how Phineas is doing after a long time to rest. Observe the return to baseline after the resting time. Glucagon has kicked in, and the liver has converted enough glycogen to release glucose for the blood sugar levels to recover. Phineas is now back at rest, but his glycogen reserve has depleted. I suggest we repeat the workout again, but this time we will follow the blood sugar, insulin and glucagon levels. Increase the exercise intensity again. Let's wait 15 minutes. Observe the variations in the physiological variables. Why do we see a small dip in the blood glucose levels? You start to master the concept. To keep the sugar level stable, the secretion of glucagon lead to the liver converting stored glycogen into glucose for release into the bloodstream. This is called gluconeogenesis. Let's keep the exercise up for a while longer. Wait another 15 minutes. Observe the further variations in physiological variables. Oh, what is happening there? Why is the glucagon not able to compensate for decreasing blood sugar levels this time? Indeed, the glucagon still binds to the liver to deliver the message to keep gluconeogenesis up and rise blood sugar levels, but there is no more glycogen reserves to use. The body will go into a state of hypoglycemia. Let's fix this. Let's give Phineas a sweet snack. Wait another 15 minutes to see the effect of the snack. Observe the effect of sugar intake on physiological variables. Look at that. That was a very sugary snack. Why do you think insulin was secreted if the body was actually in need of sugar? You get it. The massive influx of sugar raised the blood sugar level very fast, crossing the threshold where insulin would be secreted to store the excess, despite the body being in need of sugar at the moment. Insulin and glucagon do not act to counter each other, but in synergy to fine-tune the consumption and storage of glucose. Observe the final state after an hour of exercising. Looks like the body is doing fine and the variable are stable again thanks to the additional sugar intake provided by the snack. Nice job, we were able to avoid our previous issue with Phineas suffering from low blood sugar levels. You've restored homeostasis. Now that you have seen the process of homeostasis, which of the other processes below do you think are under homeostatic control? Breathing patterns are indeed under homeostatic control. Sensors in the aorta and carotid detect low levels of oxygen or high levels of carbon dioxide in the bloodstream, sending a signal to the brainstem. The medulla then communicates to the diaphragm and the intercostal muscles to take deeper breaths, leading additional gas exchange in the lungs. Once the oxygen and carbon dioxide levels are corrected, the aortid and carotid bodies will complete the negative loop by stopping the control center from activating the effectors. Now that you have seen the process of homeostasis, which of the other processes below do you think are under homeostatic control? pH sensors in the blood vessels are able to detect acidosis and alkalosis, when the blood pH is respectively too low or too high from the neutral value. Those receptors will ring the alarm in the brainstem, which then takes a decision to activate the effectors, either the respiratory system to increase or decrease gas exchange in the lungs, or the kidneys to adapt the proton exchange at the blood filtering sites. Once the pH is corrected, the pH sensors will stop signaling to the control center, thus fulfilling a negative feedback loop, and the body returns to equilibrium. This is a system under homeostatic control. Congratulations, you are now well acquainted with the concept of homeostasis. Next time you are in a situation inducing stimuli to your body, trying to think about the regulation processes in place that would be triggered to maintain the delicate balance. Congratulations, you have completed the simulation. We hope you enjoyed it and you feel wiser now.